Now, anybody know any properties of water, any other than it's less dense? What other things do you know about water? Yeah.
It's sticky.
It's sticky. That's that part of that hydrogen bonding. Water's sticky, right? Did you know that? Are you ready to answer that? Yeah. Okay. Yeah.
Water is a solvent.
It's a universal solvent. That's right. Let's talk about why that is. Let's talk about why that is. So let's focus on that right now. The property of water for it to be a solvent. Water's solvent property. Okay, so water is polar. So there's two kinds of molecules. Two kinds of molecules we talked about. Those that are polar and those that are nonpolar. Now this is going to be extremely important. All right. The nonpolar ones, they could be oils, they can be lipids, etc. But they share evenly. Do you remember that? Evenly sharing electrons. Water has polar bonds because water is the example of polar bonds. These are polar bonds because they're not evenly sharing. And I think the example we talked about was your big brother sharing a car with you, right? It's not going to happen very often, but he will share because he'll have to because mom and dad are going to make him. But he's not going to like it, and you're not going to like it. So that's what happens here, is that this becomes partial negative because it doesn't share those electrons very well. It has that extra negative charge. And then these become partial positives. And that's the whole point of how water aligns. That's why water is sticky, right? That's why someone else mentioned, let me as a side note, because it is kind of important. Water has surface tension. We talked about that with the spiders walking on the water. And that's because the water, what does water do? As it sits here, it lines up like this, right? Because water has that hydrogen bond, the spider can walk on top of it. Does that make sense? So water has that hydrogen bonding, so water can line up, and that spider can just walk right here, right on the top of the water, because the water holds together. Also, that's why when you try to pour some water from a cup, do you ever notice it bulges out a little bit just before it lets go? That's just the tension, that surface tension. This pulling, it comes from this hydrogen bonding pulling, the molecules pulling on each other. Yeah, it just as you're pouring, if you can look, you can watch it. You can go home and do it when you're pouring a glass of water. Just start to pour it. Just go real slow. You'll see the water start to bulge over the lip, but not fall yet. What stops that water from falling? The molecules are pulling on each other. They're like, no, don't leave me. And as they pull on each other, they hold each other up. That's the surface tension, all right? All right. But now let's look at water's property of being a solvent. A solvent is something that dissolves a solute. My understanding is you went over this with Mr. Custer's class. Did you?
Yes.
Well, there's a rule that you may not have covered in Mr. Custer's class. So we talked about two rules, right? Atoms want a full octet, atoms want to be neutral. Molecules and atoms want a full octet, atoms want a full octet, and molecules want to be neutral, so do atoms. We're all good with that, yes? All right. There's another rule about solvents. It turns out that, and this rule I love because all kids love this rule because it rhymes almost. Like dissolves like. It's easy. I love easy rules. Don't you love easy rules? Easy rules make life fun. Like dissolves like. I would write that down. I would know it. I would memorize it just like I did the other two rules. Because if you remember it, it'll be easy. Just like opposites repel, opposites attract, and like charges repel. This is one of those fundamental rules. All right. What that means is if you have a nonpolar solvent, it's going to dissolve what? Other nonpolar things, right? Remember what dissolve means. Let's talk about again what dissolve means. You have some substance, let's say sodium chloride, and let's make a cube because we all know now it's a cube. Na plus and Cl are all in the lattice, just like with water. The sodium and the chloride, they attract each other, but this is a full charge, so they attract each other much more strongly than the hydrogen bonds do, right? So, but you can take that salt and you can put it into water, and what happens? It dissolves, and this is what happens. And you have this. Open up your study guides. Open up your study guides. And there's some answers that you're going to have to answer. I'm actually giving you the answer here and now. So, go to the water page, the one I pointed out the other day, top right-hand corner, right? What you have is Na plus. Let's pay attention because I want you to do this. I don't want to do it because I know this. I don't need to do this. So we're going to put salt and water, and what happens is you have Na plus and you have a Cl minus. Well, what's water going to do? What part of water is going to point towards the plus? What part of water, this is water here, the oxygen. Why did you say the oxygen?
Because it's a negative charge.
This is a negative charge. That's exactly right. You got it. It's a partial negative charge. I love that. Excellent. So the oxygen is going to point towards the sodium. It's going to get in between them. Do you see that? It gets in between. Do you agree that they're in between? It surrounds them like somebody here is playing football. Oh, they're gone, I guess. But like football players try to get in between the person carrying the ball and the end zone, right? They surround them like a rugby match or some other game where... Well, what's pulling them? Why is this happening? It's the same thing as that magnet that we had in the previous example. These positives and negatives align themselves to surround it because they're negative opposites attract, right? But here's a negative, so what's going to point towards the negative? Chlorine is negative, so yeah, the hydrogen is going to point towards the negative. The hydrogen is going to point towards the negative, and so you'll have, oops, that's not going to. So what happened to that poor chlorine, that chlorine that used to be with the sodium? Is it with the sodium anymore? Why is it not with the sodium?
I you took it.
Is the sodium still there?
Yes.
Yeah, it's still there. The sodium's still there. If you're wondering where it is, here's the sodium. It's Na. And is the chlorine still there? Sure is. There it is. It used to be sodium chloride solid. Now it's sodium chloride in water. You can't see it, right? You put salt in water, can you see it? No, you can't see it. You can taste it. That's because the sodium and the chloride, they react in your tongue. They have a chemical reaction which sends the signals to your brain saying, hey, there's salt in this. So that's your body having chemical reactions on the tongue and your mouth, letting your brain know that there's salt in this. But even though the salt is there, you can't see it. We call that dissolving. Now, this is going to be weird. What I'm about to say is going to be weird, but think about this. Dissolving is a physical change. You're not bonding the sodium, are you? You're not bonding with you're not sharing electrons now. Is that correct? You're not sharing electrons between the oxygen and sodium, or the chlorine and the hydrogen. The only thing you're doing is surrounding it. So because you're not sharing electrons, because you're not exchanging atoms, if the hydrogen left and the chlorine came in, you had chlorine bonded to oxygen, then that would be a chemical reaction, a chemical change. But because you're not fundamentally changing it, we call it a physical change. Let me give you some more evidence of this. And you could do this at home if you want to try it. We don't have time to do it in class. I wish we did. Actually, we might be able to have to do this when we do the next lab. So actually, that might be part of the next lab. It might be a good idea to do that. So if I went ahead and dissolved salt or sugar in water, okay? It doesn't have to be a lot of water. It could be a little water, just add a little sugar. You know about saturation, right? I shouldn't have to teach you about that. You should know that from Mr. Custer's class. I give you a small beaker, and I put a little bit of water in it, and I put a little bit of salt in it, and I put just enough salt, sodium chloride, or sugar. Sugar does the same thing, will dissolve in water. Water dissolves both sugar and salt. Put it in there. It disappears. So you're not sure if you have a phase change, which we know phase change is not necessarily a chemical change. But it's a physical change itself. But if I add heat, right? If I add heat, yes, this is fire, deal with it. If I add heat, what do you think is going to happen to that water? It's going to boil, right? We're going to boil off the water. The water's going to do a where? Go from liquid to gas. So it's here. If I took a little circle of it, let me. You know what? I can do something interesting. I can zoom in, and let's draw water here. It's H2O here. Do you see that? When it leaves, it's going to leave as what? H2O. So it's going to go from liquid to what? Gas. So we're going to call that boiling. That's what's happening. It was H2O in the water. It's H2O in the air. Is that a chemical or physical change? Physical. Yeah. Didn't change. The bonds didn't change. So it's still water. It's just gone from liquid to gas, so we call that a physical change. The sodium chloride is where? The sodium is here. There it is. The sodium and the chloride are here. They're both going to be green. Is that understood? So it's still there, but the water's leaving. The sodium and the chloride, they're attracting each other very strongly. So it takes a lot to boil salt. Thousands of degrees. We're only going to raise the temperature here to 100 degrees Celsius at 1 atmospheric pressure at sea level. That's where we're at, right? Sea level. So there's a 1 atmosphere. I can increase it 100 degrees. What happens at 100 degrees Celsius to water? It boils. It goes to gas. All right. After a while, what's going to happen to all the water? It's going to be gone. Where's the salt?
In the bottom of the pan.
All the salt's there again. And guess what? It goes right back to being cubes. If you look at it, well, it depends how quickly you do this. If you do it slowly, you can make the cubes again. You've done this, a lot of you've done this. You've grown crystals.
Yes.
Some of you have grown crystals.
Did I grow first?
Huh? In middle school, you didn't grow crystals? Some people did.
I did.
Well, we can grow crystals here. That's what I want to do. I want to grow crystals along. The growing crystals is going to take a while. But we can just set them up in the back of the room, and we'll stick a string in. You'll see. You ever see the sugar with the on a string that forms like crystals on the string? Yeah, the sugar candy thing. Well, what happens is that as the water evaporates, and of course with that, the slower you let it evaporate, the stronger the shapes form, the better the shapes that form. And if we use Epsom salts, we'll get needles. If we use sugar, we'll get some kind of weird looking shapes, usually like cuboidal. Salt, sodium chloride will form cubes. The point is, you started with water, you added solid water, right? Or solid NaCl. You added it to water. It dissolved. Hear me, so you can make your conclusion. This is the evidence. Salt is added to water, dissolves. You heat it up. You get rid of the water, and you got solid salt again. What did we just do? This was a change, right? This is solid NaCl disappeared. Disappeared means you don't see it. It doesn't mean you destroyed it. It disappeared. The water left because we boiled the water, and now we got the solid sodium chloride again. What just happened? What did we just do to that change? Say what? Well, I added it, it dissolved. That was a change, right? Then I boiled it, I got rid of the water, and I got my solid back again. What did I just do? I reversed it. I reversed the change. What is that a sign of? If you can reverse it, it is likely a physical change. So that's more evidence that this is a physical change. Does that make sense? So I've just given you a couple lines of evidence to show you that this is a physical change. And we can do that. We'll do that with, we'll grow crystals. Next week when we do the lab on chromatography, we'll also grow some crystals, all right? They work together really well. So like dissolves like, so water turns out to dissolve salts, and that makes sense because water's polar, it can dissolve salts. Well, interestingly, it can dissolve other things as well that are not charged. It can dissolve polar molecules, it can dissolve some nonpolar stuff. So water's really good at this, really good at dissolving. What's an example of a nonpolar solvent? Well, what's a nonpolar material? It would be something that water really can't dissolve very well at all. What does water not dissolve very well at all? Yeah. Oil. Water and oil don't mix very well. Well, give me another example of something that water doesn't dissolve very well at all. Say what? Pepper. Yeah, it doesn't really dissolve pepper. I never thought of that. But okay, something else. I'm especially thinking of the girls. Almost every girl in this room knows this. Some of the boys might, because their moms, or maybe the boys do too. I don't know.
That's nasty.
I don't know what you're talking about, but
That's
what is something the girls in this room, every girl in this room, I'm pretty sure
Makeup?
every girl. Yeah, close, yeah. And almost every girl, something that the water doesn't dissolve very well at all.
That's why I just
Makeup, what kind of makeup specifically? Waterproof makeup is good. What's up? Lipstick, mascara, something else. Come on, guys. Nail polish. Who said that? All you girls should be ashamed of yourselves. Shame. But you have friends that do. There's one right here. You're wearing with nail polish. Why do you use nail polish? Yeah, there is waterproof makeup. That's true. That's because that makeup is nonpolar. That's why it's waterproof. It doesn't dissolve in water. Water does not dissolve it. You have to actually use a polar molecule, a polar substance like some kind of cream or fat, right? Because fat's non-polar. If you use any kind of like some kind of lipid, you can take off that waterproof makeup. But I was thinking more nail polish. Nail polish is not, doesn't come off in the rain, does it? You can't, it's hard even to scrape it off. You have to sit there and scrub it. You could use water. Water will dissolve it. It just takes a lot of water and a lot of scrubbing. And even then it won't come off well. Do you agree?
Need some nail polish.
You need nail polish remover. What do you think nail polish remover is?
Alcohol.
It is acetone. Alcohol would work too, by the way. But it is acetone, is correct. But is it polar? Is acetone polar or non-polar? Who says polar? Raise your hand. Who says non-polar? All right, why do you say non-polar? So let's,
I know.
yeah,
Non-polar, like dissolves like.
like dissolves like. Excellent. Like dissolves like. So water does not dissolve. Let's do the logic. Let's do the logic. Walk through the logic. Walk through the reasoning, right? Walk through the reasoning with me. This is reasoning, yeah? Claim, evidence, reasoning. Walk through the reasoning with me. 1, like dissolves like. So we're clear on that. Okay. 2, the second point here is water is polar. Yes? So that's 2 things. So polar dissolves polar, non-polar dissolves non-polar. See, that's a perfect question to ask, isn't it? Thank you. I'm telling you, there's 5 to 10 kids in the room that are like, what is like dissolve like mean? And you're the only one to ask it. I was wondering when someone would ask that.
It means polar.
Everybody assumed yeah, some people got it right away. I got that. I understood that. But I knew some of you didn't get it. And I was wondering, was somebody going to ask it? You guys got to ask questions. Good job. Good job. All right, water, like dissolves like, water is polar. All right, 3. 3, water is polar. Water does not dissolve nail polish. Do you agree? All right, so this is all true. We're going to assume these are true, but no one disagrees with any of this. All right, so
I think you spelled dissolve.
Did I do wrong?
I was tripping
my bad, my bad,
on both of them.
my bad.
You want me to go check if they got locked?
It'd be funny if they got locked out. I would laugh at that. All right, water in the rain. Water does not dissolve nail polish. Do we all agree with that? All right.
State that sounds reasonable.
Water is polar. Like dissolves like. So what do we say? So therefore, can I do this? Can I put a triangle? This means, therefore. All right?
Man, what?
Are we good?
You made that up, or that's like real?
That's real. This is from geometry. This is again, it's a symbol that means therefore. Are we good? Like dissolves like, water is polar. Water does not dissolve nail polish. Therefore, nail polish is non-polar. Everybody okay with that?
Yeah. Hey, right there.
But we didn't end there, did we? What did we do? We said what? Now, that was step 1. Part 2, this is part 1 up here.
What is
Part 2,
what is made of?
1 we said acetone dissolves nail polish. right? Therefore, what?
Acetone is nonpolar.
Acetone is nonpolar. Okay? Are we getting this? So it's just real simple. We know like dissolves like. If we know that's true, and we know that that means that things that are share electrons unevenly, they have positive, partial, negative. They will dissolve things that are polar, and they'll dissolve things that are ionic, by the way. We know that because we saw it with sodium chloride, right? So polar molecules like water will dissolve salts, they'll dissolve some slightly nonpolar things, they'll dissolve polar things. That's why we call it a universal solvent, because it can dissolve all these things. Acetone won't do anything to salt. It won't mix with salt at all. Acetone won't mix. Water will mix with acetone to some extent. They'll mix. Water will mix with acetone. Water will mix with oil a little bit, not well, but a little bit. So it turns out that water's a really good solvent. It does a good job, and that's why we use it in buckets and mops. Because when we put it on the ground, it dissolves, it hydrates, it surrounds, right? All these different particles on the ground that we can't sweep up because they're too small. Does that make sense? All right. Question?
I was gonna say why when you started talking about your second part, it felt like way more.
Go ahead.
It felt like way more simple. But at the beginning, there's so much detail that you're going into. Felt like it's not.
At what beginning?
Like when you first started talking about nonpolar, it was complicated.
Well, I think what you're finding is that when you go into detail and you understand the fundamentals, what you're able to do is understand the process. And if you understand the process, then you can answer any question. If I would just tell you, if I sat here and just told you, look, two DNA molecules, right, they're held together by hydrogen bonds. If I said that to you, right, and I told you two hydrogen bonds or I told you acetone, like dissolves like. I just said that. Without explaining to you why. Without explaining to you the reasoning, right? I think you would be less prepared for any questions that come for you in the end of the year. If you understand the reasoning, some of the detail, and believe it or not, I left out a lot. And you know what I feel like doing for you? To show you how much I left out, I feel like giving you an assignment in Khan Academy. Your first assignment in Khan Academy being electronegativity and showing how much detail I did not go into. So I think I chose based on experience just the right amount of detail. I hope I did for you. But the key was what? That you have some understanding of the process. And if you understand the process, you can apply to whatever question comes to you. Because I don't write your questions for the state exam, right? I don't write your SAT questions. I don't write your ACT questions. I don't know what you're going to be asked in AP Chemistry or in your AP exams in sciences throughout your career. All I can do is give you a good process so that you can answer any question that comes at you. Is that fair? Okay. What do you guys think? Are we done with this then? We got this idea of how water dissolves things, like dissolves like, polar, nonpolar. So those are qualities of water. They're very important. I guess